Hello. So today we're going to be starting on one of the most common probability distribution in statistics, that is known as the Gaussian distribution. So later on, like in the future lectures, we're actually going to be looking at a lot of different probability distributions, including this one. But right now I thought to just give a simple introduction to it, as well as go through some proofs that this distribution makes use of. Having said that, let's actually get started with this. So we're looking at the Gaussian. It's also called the normal distribution. So when we're talking about this as a probability distribution, we actually expecting it to be a probability density function, in a manner of speaking. If you don't remember what that is, please just watch the previous lecture. So the Gaussian distribution, just to start off, is actually represented by the following formula, right? So I'm just going to start it off. So we have n, which represents normal here, of x, and it's parameterized by two things. The first thing it's parameterized is the mu, which means the mean, and the variance, which is represented by sigma squared, right? This is how we parameterize this. And what is this equal to? So this is 1 over 2 pi sigma squared, right, to the power of a half. So the square root of this multiplied by the exponential of 1 minus 1 over 2 sigma squared times x minus mu squared. So essentially this is the formula for the Gaussian distribution, right? So we say that this is a probability density function, and it is represented by a couple of things, so I'll just write them down. First of all, we have mu, which is representing the mean. We have sigma squared, which is representing what we call the variance. So if you remember from the previous lecture when we're talking about the mean, which is just the average of a function, in a manner of speaking, and the variance, as well as something called the standard deviation, which is just represented by sigma. So standard deviation from the mean, deviation. And we also have something else which is not shown in this formula, but you can actually substitute. We represent it by beta, which is essentially equal to 1 over sigma squared, and we call this the precision. So we will discuss what this is in detail later on when we actually look at this distribution in more depth. Right now we're just going to look at its properties and try to prove why we're saying that these certain properties hold, essentially. So having said that, let's actually have a visualization, in a manner of speaking, of what this actually looks like. So I will start by drawing this. Okay. So when we're talking about let me use orange. So we have something like that. Okay, so it looks like a bell, in a manner of speaking. So, and this part here is what we call the mean, mu, and what this is representing essentially is what we said, n of x given parameter x by mu and sigma squared. So this is essentially what we're looking at, and this is our x-axis, right? And so this is our probability density function, And essentially what we're saying is, when we're looking at this function and we look at the area under this function, we're saying it's actually this area should be equal to 1, right? So expressed in another way, we're saying that the integral from minus infinity to infinity of the normal distribution, which is parameterized by these two things, with respect to x, should be equal to 1. So that's essentially what we're saying here. So one question you might have, of course, is, can we actually prove this? We're making this assertion here, the statement, this bold statement, but of course what we want to do is prove this, right? And how do we actually go about proving this? So let me actually do that on a different page, probably would be better. Okay, so let's remember the formula again, written here for the Gaussian distribution. So after remembering it, now we can actually go about proving this thing. So let's actually assign something. We're gonna make an assignment here, and we're gonna say I. Let me use the same color black here. We're gonna say I is equal to the integral between minus infinity and infinity of the exponential of minus 1 over 2 sigma squared x squared dx, right? So this is the, what we call this, this is one of the components of what we're calling the Gaussian distribution and so forth, right? So if you look at what we have here and you look at what we have over there, you see that they're actually quite similar. So we're just assigning this to I. This will all become clearer when we actually reach the end of this proof. So this is what this integral is, right? So let us actually define what we I squared, right? So by I squared, I mean we're actually multiplying this integral, so from minus infinity to infinity of the exponential of minus 1 over 2 sigma squared x squared with respect to x, right? And we are multiplying this again by the same thing, exponential of minus 1 over 2 sigma squared. Let's just call this y squared, where y and x are the same thing essentially, dy. Right. So we are trying to multiply those two integrals, and one of the first things that we can actually look at is, well, if you look at this integral, this is a closed integral in a sense with these boundaries, I mean. So what we can do is, this will actually evaluate to some value, like call it a, right? It's going to evaluate to this value. So since it's going to evaluate some value, what we can do is rewrite this integral. Since we can actually multiply this, it's the same as multiplying this whole integral by a, right? So we can actually write it as a times the integral of infinity to minus infinity of exponential of minus 1 over 2 sigma squared x squared dx. So this is one way we can do this, and we can actually have the a be inside this integral, right? So this is the same as just saying having this inside, minus 1 over 2 sigma squared x squared dx. So now that we have this a inside, let us actually expand it out. So I'm doing it this way just so that you can follow every step to understand essentially what we're trying to do here. So if I now expand a out, we actually have integral between infinity to minus infinity, and another integral between infinity to minus infinity. Now we have this, okay, let me write it this way so that it's clear. This is our a, right? So this is another integral between minus infinity to infinity of the exponential of minus 1 over 2 sigma squared y squared, right, dy times the exponential of minus 1 over 2 sigma squared x squared dx, right? So this is what we have. So if we actually just reorganize everything here, we'll end up with a double integral from minus infinity to infinity, right, of the exponential of minus 1 over 2 sigma squared x squared dx. Actually, let me not put this here yet, times the exponential of minus 1 over 2 sigma squared y squared dx dy, right? So this is where we are at this point. And then after this step, what we want to do is, expand this term essentially. So again, we have the same term there, and we can actually write this as just exponential of minus 1 over 2 sigma squared x squared minus 1 over 2 sigma squared y squared dx dy. So let me just, so this is, we can do this of course because if you have this, let me just, so e to the power a times e to the power b, this is essentially equal to e to the a plus b, right? So since this is actually the case, we should be able to do something like that. So in case I make any, I might make some algebraic mistakes here, but you can just follow through what's happening and get an idea of where we're going with this, essentially. Okay, so now that we've established this sort of integral that we have in this case, let me just make sure that everything is in order. So we have minus 1 over 2 sigma squared x squared times. Okay, yeah, it's fine. Everything is okay. So just trying to double check if I made any algebraic errors over here. So I think it should be okay. Okay. So now that we've reached this point, right, if someone actually asks us, like right now, of course, you might not understand where we're going with this, but just keep on going because it's all going to come up together towards the end. Why we're doing all of this, just to prove that this is a probability density function that sums up to 1, right, when we're talking about the normal distribution. So now that we've gone through this, we want to, like, by multiplying this, we have established that this should be equal to I squared, right? That if we want to compute I squared, we have to actually do something like this. So now that this is established, the next thing we need to do is look at something that's called like polar coordinates. We need to convert these coordinates to what we call polar coordinates, and this is more of a refresher because I'm assuming that you are familiar with calculus. So I'm going to just, let me do this on the new page, yes. Okay, so if you remember from calculus or trigonometry, whatever, if we are given something like this, whereby we denote this area from here, this is x, right, up to this point, and up to this point we have y, and we call this theta, and this is r for like a radius, right? So one thing that we know is that, like, if we want to find, for instance, the cosine of this angle, right? So cosine of theta, how would we do this? Let me just write it as cos theta just to be simple. So we would do this by saying this is equal to the adjacent over the hypotenuse, right? So cos theta is equal to x over r, which means that x is equals to r cosine theta, and then sine theta is equals to y over r, so that's adjacent over hypotenuse. Opposite over hypotenuse, not adjacent. So this should give us y is equals to r sine theta. So by doing this, we are converting this Cartesian coordinates to polar coordinates, right? To what we call polar coordinates. And by using the Pythagoras theorem, we can essentially assert that x, okay, maybe I should use the same color here just for consistency. So x squared plus y squared is equals to r squared, right? So these are just things, this is just a refresher from calculus. So what we want to do here is replace the integral that we expressed in the Cartesian coordinates. We want to actually replace it by an integral in the polar form, because once we do that, then it will be much easier for us to simplify it and actually complete our proof here. So let's actually take a step back and understand what's happening here. So normally when we're given a double integral, right, over what we can call maybe the rectangular space or whatever of f x comma y dA, right? So here dA is just talking about dx dy, which is essentially the same thing that we had over here. So this is essentially our dA. That's the dA we're referring to, right? And all of this is for the goal of, converting all of this into polar form, essentially. We can actually rewrite this. We can rewrite this as the integral, right, of f r cos theta, comma r sine theta dA. So we can rewrite this integral in this form, and further on we can just simplify it in this manner, and then we are actually writing this in the polar form, like using the polar coordinates, and we can write this as f r comma theta, and instead of having because let me just reiterate this point because this is important. So as you can see, this integral is essentially fx comma y dx dy, right? But now that we converted it into polar coordinates, it's no longer just what you would expect it to be, like dr d theta, but rather it's r dr d theta, right? So if you're familiar, of course, with multivariable calculus, you probably know why this is the case. But for those who aren't, I'm just going to give two ideas that will help you, understand this better. So the first one is more of a formula when you're just trying to change the variables of a double integral like this one. So it's called the Jacobian, and you can look more into this if you'd like. The Jacobian change of variables. And basically what it says is that when we're changing this variable, so you're given dx comma y, and in our case we want to change them to dr comma theta, right? We would look at the Jacobian matrix for this. So we got dx with respect to r, dx with respect to theta, dy with respect to r, and dy with respect to theta. And we're going to take the determinant of this, essentially. So the determinant of a matrix, so determinant of A, this is more like a refresher again. Let me actually write this in a different color. So if got A is equals to A, B, C, D, then the determinant of A is equals to AD minus BC. So this is just a side note for you in case you want to know how to compute the determinant. So this Jacobian change of variables is going to give us the extra, is supposed to give us the extra component that is supposed to be in our integral. So essentially, after doing this, let's actually find this derivative. So what is the derivative of x with respect to r? So where is it? So x is equal to r cosine theta. So the derivative of x with respect to r is, of course, cosine theta. So let's write this down, cos theta. And then the next thing when calculating is the derivative of x with respect to theta, right? So derivative of x with respect to theta, this is minus sine theta. So the derivative here is minus sine theta. And then over here we've got the derivative of y with respect to r. So I'm just going to fill this down so that, and this is r. Sorry, this is, I made a mistake here. This is minus r sine theta. I forgot the r for this part. And then this is sine theta. And then this is r cosine theta. Right? So essentially what we're calculating here is this times this, which will give us r cos squared theta, minus this times this, which will give us plus r sine squared theta, which is r cos squared theta plus sine squared theta, which is essentially equal to r. Why? Because this evaluates to 1. So these are just one of those trigonometry rules that you need to remember. This evaluates to 1, so this is r. So what this is telling us is that the extra term that we need to add in this integral is r, like r d theta. So this is known as the Jacobian change of variables. And there's a whole proof as to how this came to be, but I'm not going to go through it right now. I'll probably give you maybe a different intuition on what we're doing here. So if you're thinking of dA from the Cartesian place, so you're thinking more of a, let's say you're given this kind of rectangular thing here, and you can express yourself this change in x, right, and this change in y. This is how you view it in this plane, right? A change in x and a change in y. And then you are essentially able to say that, okay, if you want to compute the area here, you are essentially computing dx dy. So that's how it works in this place. But what we're doing here, once we move on to the polar coordinates, right, so when we're looking at this was a zoomed in version of what we would see maybe in this Cartesian plane, this Cartesian coordinates. So probably this is a zoomed in version of this, a small change in x and a small change in y. But once we go into the polar coordinates, now we're looking at things in this form, right? So this is how we're looking at things at this point. And then we're looking at a small section here to see by how much did this part change, and by how much did this part over here change, right? So we're looking at this small section where this is the arc, and this is kind of like the change in the radius, and this is the change in the arc. So how do we actually express this? So let me actually draw this down over here. And then we have our small segment over there. So if this is our radius r, right, then this section over here we call dr, change in r. But now what's the change in this part over there? Of course it's not theta, because this is the arc, right? And then what is the arc length formula? Well, the arc length formula says that we're supposed to multiply if we're using the arc length formula, we can say the arc or surface area is equals to r times theta, right? That's essentially how we compute this. So which means this area here, of course we know this is a small change in theta, but since we're looking at this whole part, this arc, we know this is r times d theta. The change in theta is d theta, but because of the arc length formula, that's where this r comes from. So that's another way we can actually look at this, and we can assert that when we have this integral, this double integral here, it essentially evaluates to what we see over there, right? So this was just a note for you to understand this point. So let's move on to the next page. Okay, so now that we're here, right, now that we made this point in a manner of speaking, we can finally replace this integral that we had before. So let's write it down again. So what we had said was the integral between minus infinity and infinity, and the integral between minus infinity and infinity of the exponential of minus 1 over 2 sigma squared x squared minus 1 over 2 sigma squared y squared dy dx. Oh, sorry, should say dx dy, I guess, for consistency. Okay, actually we can rewrite this, right, in another way. We can actually express this as, I'm going to just try to quickly write this. So we got exponential of minus 1 over 2 sigma squared x squared plus y squared, right? We can write it in this format if we want to, essentially, then dx dy. But now we're going to make that substitution that I was just talking about a moment ago. So we can actually express this as I'm not going to write the limits of the integration right now because they're going to change. But we said r squared is equals to x squared plus y squared, right? Just before. So what we can do is replace this with r squared, but since we're going to be integrating with respect to the r and d theta, we should make sure to add that r value. So this becomes the exponent of minus r squared, because x squared plus y squared is r squared, right, over 2 sigma squared. We multiply this by r, then dr d theta, dr d theta. Okay, because of the Jacobian change of variables, we need to have this extra r. Now, what are the limits of the integration? So we first start the limit of the integration for the r term, and this should be easy to evaluate in this case because the smallest radius we can have anyway is 0, and this can go all the way up to infinity. And for the theta, of course, it should just be from 0 to 2 pi, since it's going through a full revolution in this case. So that's essentially how we can represent this. So now that we have this integral, we can actually separate this further. So we can integrate the inner part first, then integrate the outer part first, since that's how we perform double integrals. So we can write this as 0 up to infinity of the exponential of minus r squared over 2 sigma squared multiplied by r dr. Then we can multiply this by the integral between 2 pi and 0 of d theta, right? And this will just evaluate to 2 pi. So this will evaluate to 2 pi. So we're actually done with this integral over here. Now for solving this other integral, we can do so by substitution. So what we can do is substitute, say, u is equals to r squared. And by making this substitution, then we can say this is the this actually means that du dr is equals to 2r and du is equals to 2r dr, right? That's what du becomes here. And r dr becomes du over 2, right? Because we're going to substitute it here. So essentially we can say this is equal to the integral from 0 up to infinity of the exponential of, so instead of minus r squared, we now have minus u, right? Because we substituted u to be r squared, divided by 2 sigma squared, and then multiplied by 1 over 2 du. So we should be able to do that at this point. And then now that we've done that, the next logical step, of course, is to evaluate this integral, to actually compute this integral. So we can take this 1 over 2 out, right? So we can take this one and have it come out here. And this is equal to, so now that we are actually integrating this, we can say this is 1 over 2 times, right? So what's the integral, like how do we integrate what's, we need to take the derivative, the inverse of the derivative of what's inside, rather, I should say. And this is what we're actually going to make use of in this case, right? So where was I? So I was here. So the first thing is, okay, we are taking this integral with respect to u, right? So if we take the derivative of what's inside of this exponent, what are we left with, essentially? This is one of the questions that we need to ask ourselves at this point, right? Okay, so what we have here is wait a minute, I think I left something out here. No, I think it's fine. So what we have here is we can essentially evaluate this as minus 2 sigma squared, right? And the exponential of minus u over 2 sigma squared, right? Sorry about that. I just had something I had to take off. So yeah, back to what I was talking about. So we have this, we're in this position, and this is from 0 up to infinity, right? These are our limits. And just for the sake of it, let's take, because here, don't forget, we are multiplying by this integral which evaluates to 2 pi. So we need this 2 pi back. So it should come down here, multiplied by 2 pi. So this 2 and that 2 will cancel. So essentially what we're left with is, so if we substitute infinity here, like we'll have the exponent of minus infinity, and this whole term we evaluate to 0, right? So what we would have is 0, right, minus, and then if we substitute if we substitute 0 instead, the exponent of 0 is 1, and then we would have minus 2 sigma squared times pi, and this should give us 2 pi, right, sigma squared, right? So what is 2 pi sigma squared in this case? What is it that we were just computing? This is what we ought to ask ourselves. Okay. So let's take a step back. So if we look over here, we see that we started from a point where we are expressing this double integral, but we converted it into polar form so that we're able to actually go all the way down here. But we had made an initial expression where we were assigning this to I squared, right? So 2 pi sigma squared here, this is equal to I squared, right? Which means that I is equals to the, let me write this as 2 pi sigma squared to the power of 1 over 2. That's what I is in this case. So now that we have expressed that, the next thing is going back to expressing this whole equation, because it started by, let me go back again for clarity, over here. We had assigned I to be the exponent of this, so let me write it down again so that we can see it over here. So we had said I is equal to the integral between minus infinity and infinity of the exponent of minus x squared over 2 sigma squared dx, right? So this is what we had called I over here. So x squared over 2 sigma x squared dx, right? So this is what we have here. So this is what we called I, and we also discovered after computing this integral that I is actually equal to this value. This is interesting, because now when we're expressing this function from minus infinity to infinity of the normal distribution of x parameterized by mu, comma sigma squared dx. We had said this is equal to 1 over 2 pi sigma squared to the power half. This is just the formula of the Gaussian distribution. So minus infinity up to infinity of the exponent of minus y squared over 2 sigma squared dy. So, this should be minus x minus mu, right, over 2 sigma squared dx. This was the initial Gaussian formula that we introduced in the beginning, right? X minus mu squared over 2 sigma squared. But if we just say that y is equals to x minus mu, then we can actually rewrite this as 1 over 2 pi sigma squared to the power 1 over 2 integral of minus infinity to infinity of the exponent of minus y squared, right? There should be a squared here, over 2 sigma squared dy. But from this here, we know what this is equal to. This is actually I, right? So this term over here, this term here, this is I from here. And we also know that this term over here is I, because we've proven it as well, right? So what we're left with is a situation where we have I over I, and this should give us 1, right? So as such, we have actually proven that this distribution should be summing up to 1, which is, we should convince you that this is a normal probability distribution and stuff like that. It has the properties of 1. So now let's actually move on to another page, because now that we've proven this, we need to move on to some other properties that we expect to have from the Gaussian distribution. So first of all, let's talk about the expectation. We're talking about this mu and we're calling it the mean and everything, right? So we look at the expectation of the Gaussian. What do we see here? When we compute the expectation of x, right? This is equal to the sum from minus infinity to infinity of the probability distribution itself. So if you remember the definition of the expectation from the previous video, it's the probability distribution itself times the variable itself, dx. And we're going to say this is mu. Why? Because the expectation is supposed to give us the average value of some function and stuff like that. And when talking about the Gaussian, this actually boils down to the value mu. Why? Of course, the next question you might ask yourself is, prove it, right? Which is essentially what we're trying to do. So we want to prove these different properties of the Gaussian distribution. Of course, I'm not gonna go through all of them. Like for instance, there are some more assertions that we can make for the variance or the standard deviation and so forth, and you can work through them yourself and prove these things to yourself if you need to. But this is just to prepare us for things that are gonna come into the future, so that we understand why things are the way they are, right? So I'm going to continue on this. So when we talk about this, so let's actually again expand it. So we have expectation of x, right, being equal to the integral from minus infinity to infinity of 1 over 2 pi sigma squared times, to the power of a half, times the exponent of minus 1 over 2 sigma squared multiplied by x minus mu. So we're just rewriting this formula, but now we're multiplying it by x, then dx, right, as per the definition of the expectation for the Gaussian, right? And we want to prove all of this will boil down to being mu, right? So what we can do is, let's actually make some kind of substitution here. Let's just say y. Let me write this in a different color. Let's choose something else, from green maybe. So y is equal to x minus mu, right? This is the substitution we're going to make. Now let's rewrite this formula. So it becomes expectation of x is equals to the integral between minus infinity and infinity of 1 over 2 pi sigma squared to the power of a half times this exponent minus 1 over 2 sigma squared. This becomes y squared, right, since we make this substitution, times, and then here we've got y plus mu, right, dy. If we substitute in place of x, if we put y, that's what we're going to have here. Okay, so let's just ignore this term for now. So I'm just going to put this term outside, so, and just ignore it for now, since it does not actually depend on y. So what we end up with is this integral, and then I'm actually going to expand. I'm going to expand out these terms over here. So this is integral between minus infinity and infinity of the exponent minus 1 over 2 sigma squared y squared times y plus the integral from minus infinity to infinity of the exponent of minus 1 over 2 sigma squared y squared times mu, right? All of these are with respect to y, of course, dy. So this is what we're left with. Okay, so let's actually look at these functions to begin with, okay, because this is an interesting part. So one property that we know about what we call like when we're talking about even or odd functions is that when we're looking at odd functions or even functions, for instance, at the start, and we take the integral from minus infinity to infinity, it's probably the same as taking the integral from 0 to infinity and multiplying by 2 in that case. But in case of odd functions, if it's an odd function, then the integral from minus infinity to infinity should actually boil down to 0, essentially. And why do we say something like that? Because odd functions, of course, should have the following property. So let's look at the property of odd functions. One property that they're expected to have: if you take f of minus u of an odd function, this should be equal to minus f of u, right? So this is what one property that we are going to make use of here, right, in computing this integral and simplifying the work for ourselves. So if we look at this function, right, so what you can do is try to actually substitute the values here and actually see if it all boils down to the same thing, essentially. So let me actually do it actually to make it easier for you. So let's look at this function here, which is a function of y. So we can say that f of y, right, is equal to the exponent of minus 1 over 2 sigma squared y squared, right, multiplied by y. So if we take f of minus u, this should be equal to the minus here, because here was y becomes minus u, so let's put the minus over there, and then we got minus 1 over 2 sigma squared u squared multiplied by u, and this is actually equal to minus f of u, right? Because f of u will be the same as this but with a y instead. So we have proven that this is an odd function. By proving that this is an odd function, what we're doing essentially is saying it should follow a structure like this one, right? When we're computing the area of this function, we look at, for instance, this over here and this over there, and then this is the property that it follows, such that the integral here will cancel out with the integral that we might have over here, which is why it all sums up to 0, right? This is the reasoning behind this kind of, having these odd functions. So now that we've proven that y is actually an odd function, we can actually say that the integral of this thing should be 0. If you're still not convinced of this, then of course we can actually expand this integral further and just say, okay, let's take the integral of minus infinity up to 0 of the exponent of minus 1 over 2 sigma squared y squared y dy plus the integral from 0 up to infinity of the exponent of minus 1 over 2 sigma squared y squared y dy. So we can do that, but we can actually rewrite this, because another thing is that if we have f of minus x, because we know this is an odd function, is equals to minus of f of x, right? What this means, what this is actually saying is, if we take the integral from minus a up to 0 of f of x plus the integral from 0 to a of f of x, this is essentially equal to taking the integral of 0 to a of f of minus x plus the integral of 0 to a of f of x, right? This is how we can rewrite this expression, and by doing so we can rewrite this as the integral from infinity to 0, right? But since we have a minus, this becomes a minus y, right? So it becomes minus here. We're going to put the minus over there. Exponent of minus 1 over 2 sigma squared minus y squared is the same as y squared. Then this is y dy plus integral from 0 to infinity of the exponent of minus 1 over 2 sigma squared y squared y dy, and this is equal to 0, right? So what we have done is just proven that this integral over here, let me use a different color, that the integral we have over here, this is actually going to boil down to 0. So now we're going to just evaluate this integral, this remaining integral. So let's do that. We're running out of paper, so I'm going to open a new page. So what was it? Let me try to go back to where we were. So integral from 0 up to infinity of the exponent of, okay, right, integral from 0 up to infinity of the exponent of, what did we have? Minus 1 over 2 sigma squared y squared, minus 1 over 2 sigma squared y squared, and I think we were multiplying it by mu and dy, right? This was what we were doing. Yes. Yes. Wait. What? Oh, sorry. Yeah, it's multiplied by mu here. I had lost it for a second. Okay, but let's actually go back earlier on in our proof, right? If you remember, what we did essentially is we ignored this term, right? We just put it outside, but let's bring it back, right? We're gonna bring back this term. So 1 over 2 pi sigma squared to the power, let me write it below, I guess. So 2 pi sigma squared to the power minus a half times the integral from 0 up to infinity of the exponent of minus 1 over 2 sigma squared y squared mu dy. And of course mu does not depend on this, so we can take it outside here since it does not depend on y. So now we're left with evaluating these two things, but we already did that before. We say that this, which is essentially the same thing we're looking at down there, is I, and this is also I. So we have another situation whereby we've got this being evaluated to I, this is evaluated to I, so we have another I over I multiplied by mu. So essentially we've got mu in this case, right? So this again is I, and this bottom part is I, so I over mu, and then we get the remaining mu like we had in this case. So this is the same thing we had down here. So we've actually proven that this expectation boils down to mu. Okay, so this is another property, of course, that we're looking at when it comes to the normal distribution. So having said that, let's see if I should start on this now. Okay, let me just hint at it at this moment. Okay, so the next thing is when we're looking at where is it? If I have some expectations for, let's talk about the variance actually, and say e of x squared is equals to the summation from minus infinity to infinity of an x mu comma sigma squared x squared dx, which is equal to mu squared plus sigma squared. This is our next statement that we're making, which will mean that the variance of x is equals to, based on the variance formula that we defined in the previous lecture, e of x squared minus e of x, right, squared, which is equals to essentially sigma squared, right? This is what we have in this case. Sorry. So now that we have established this, of course we can go about proving this again, but I'm not going to do that in this video. You can take it as a exercise for yourself. It's quite helpful, of course, to prove those things to yourself, because sometimes, like, as we go on further, it will be beneficial having this kind of understanding of where all of this is coming from, as you'll soon realize, as things are going to be getting a little bit more difficult as we move on further, but it shouldn't be anything too heavy. So let's look at the Gaussian distribution over a d-dimensional vector x, right? So we have our d-dimensional vector x, and we want to define a distribution over this. So what we can do is just say the distribution of this vector, which is parameterized by mu, and this symbol is representing the covariance, right? So this is now the covariance, because now we're talking about things in a d-dimensional plane, essentially. And this is equal to 1 over 2 pi d over 2 times 1 over, so we look at this covariance matrix and we take this is to the power of a half times the exponent, right, of minus 1 over 2 x minus mu. So I'm abusing the notation a bit here, but you should just get the idea so that you can see the similarities between this and in the univariate case. This is essentially what I'm just trying to establish here. So we're actually gonna go, so let me also denote that this is actually the mean. We're actually going to go a little bit further when we start talking about statistical distributions in general. We're gonna explore this one further, but for now I just wanted you to get an idea of what it is, what it looks like, and then later on we can go into more depth and see what we're actually using this for, in a manner of speaking. So having said that, in the next lecture probably we're going to start talking about the maximizing the likelihood, I should say, for this distribution and stuff, and what it actually means, how it can help us when we are solving our statistical problems and such. So having said that, I will end this video here. Hopefully it's been beneficial. Of course, I apologize for getting a bit lost at times in all this mess that I created, but I hope you have a general understanding, of course, of how we make use of this distribution. Thank you.